In this problem, it's not oscillating back and forth, but it's going around in a circle, and it asks how long does it take to go around in a circle. So, is it clear to you that this object is traveling in circular motion? So there has to be an unbalanced force that's causing that to happen, and that unbalanced force causes a centripetal acceleration that has to be equal to v squared over r. All these things are things we've talked about, but we haven't used it in this way. The issue is that this problem asks about time. How long does it take to go around in a circle? And I think for some of you that's elusive. But is it clear that the object's traveling at a constant speed? Is that part pretty clear? It's changing direction all the time, but traveling at a constant speed. I don't need to demo that again, but would you agree with that statement? If it's traveling at a constant speed, then distance equals speed times time, right? For a constant speed, no acceleration, distance equals rate times time. So that would look like this. The distance equals the velocity times the time. We want to know how long it takes to go around once. Well, that means the distance is 2 pi r, and that would be the time for one revolution. Capital T is generally used to represent a period, the time for something that repeats itself. Would you agree that this thing is repeating itself and it goes around in a circle? So we will use a capital T to describe this as a period, and that means that T, the period, equals 2 pi r. I don't know why I switched the V for an R there, but thank you for not bringing it up. Divided by V. So I'm thinking all of these are linked together. Now first, this, we use it all the time. I want you to come to grips with that. We're going to use that all the time. So please just start putting that in part of your it's not going to be on any equation sheet. You're not going to see it on the big master equation sheet you're getting with this next test. It's not going to be on a note card. Just come up with it in your head and leave it there a lot. So I don't know, if you're having like a note card, do you have like the motion equations on that you just kind of tucked away someplace? Put this on there. Take it out when you're doing your homework, because you're going to use this a lot. And we're going to use it almost every unit coming up for a while. So just have it tucked away for a while, okay? But I think we're going to use this here. Now, I do want to say to you that any problem that has uniform circular motion, velocity gets worked into that problem pretty quickly. Can you see why that has to be true? So we have a way to get the velocity. And once we have the velocity, we can probably figure out the period. That seem pretty reasonable? All right, so I think we're working to find the velocity. But this is a force problem. And because it's a force problem, you guys realize that net forces can only tell you either the size of an individual force or an acceleration. So I think we're probably angling for the acceleration. Don't you think? All right, let's work this problem out. Let's start by drawing a free body diagram, or deciding whether it's a first or a second law problem. We should probably do that one first. Is it a first or a second law problem? Has to be a second law because it's accelerating. It's got a centripetal acceleration. It's traveling in a circle. That makes all circular motion problems a second law problem. So we'll start from there. Name a force acting on the weight. Gravity. There we go. Weight. On somebody's makeup test, they put this for their for the free body diagram. I couldn't give them credit. Right? G is a restricted letter, so you can't use capital G. So if you're going to label this, what are your options? Weight, mg. You could use F with a subscript G, that's fine, but you can't use capital G. It's a restricted letter. These are restricted letters. They can't be used for stuff because they already are assigned to things. This one's assigned to the acceleration of gravity. This is assigned to the universal gravitational constant, which you're going to learn about next week. But right now, it's assigned to something else. You can't use it there. These are okay. And I'm just going to use that. All right, name another force that's acting on the object. Tension. So, tension. Name another force acting on the object. Is there anything in contact with the object? Any surface? Any friction? Any air resistance? We said we're not doing air resistance now, so I think this is it. This is all the forces that are acting on the object. There are only two. So I need to have a coordinate system. And my first priority of a coordinate system is to align it with the direction of the acceleration. What direction is the acceleration? Towards the center. Perfect. Because it's towards the center, that means my x direction is going to have to line up like this. Because this is towards the center. I think not everybody would have put that together. But remember, towards the center. That makes y like that. Do I have any off-axis forces? I have one. Where does the 25 go? Yes, it does. It goes right there. If you didn't know that, it's because you forgot about alternate interior angles. That's where the 25 was before. So the 25 has to go on the other side over there because those are alternate interior angles. Good old geometry honors. All right, so I'm going to take the T and break up into its two components. I'm going to put a tension in this direction and a tension in this direction. And my right angle's there. Is that pretty all right? We know which one is the opposite side. That one gets sine. We know which one is the adjacent side. That one gets cosine. So this is going to be sine 25, and this one's going to be cosine 25. Are we all good so far? All right, so I'm thinking I have two net force equations. I have net force in the x direction equals ma. I see only one force in the x direction. That is T sine 25 equals mac. And net force in the y direction, well, that equals 0. But I see two forces in the y direction, don't you? I see the T cosine 25, and I see weight. So T cosine 25 minus weight equals 0. All right, we've done the force concept model. We have generated two relationships, which we hope could be used to solve our problem. So I'm going to just move some stuff out of the way so it's less distracting. And bring those two things together. I don't need anything else. Now, from this point forward, we're trying to figure out what the velocity is. So I think we got some things we can do here. First, I think we can write this one as T sine 25 equals mv squared over r. Are we okay with that? And I'm going to write this as T cosine 25 equals mg. Now, we don't know what T is, but I think we could eliminate T right now if we felt like it. Do you see how we could do that? We've talked about this, I think, once or twice, but by lining these up, I am making a suggestion that we divide both sides. Right? That'll get rid of the T on the left side, but give us sine over cosine. And on the right side, it'll just cancel out the m's. But you're going to see me do this a lot. When there's an opportunity to get rid of tension or one of these forces we don't know, dividing one equation by another equation is an easy way to wipe some stuff out. So I'm going to encourage you to do that. You don't have to. You could do substitution. You could solve one for T and plug it into the other. But we want to eliminate the forces that we don't know because we're trying to figure out the velocity. So I think one way to do that is just to divide both of those sides out. So that'll be T sine 25. And I'm writing this step out because some of you don't understand what I'm suggesting you do. But I'm suggesting we do that. Right? We're dividing both sides of an equation by the same amount. All right, well, that cancels the t's here and it cancels the m's there. Now I'll get tangent 25 equals v squared over rg. We could solve this for v. That's not a problem. What's the problem here? Which one of these things do we not know? We don't know r, but I think we do know r. There's our picture, right? R is going to be this distance. Right? Isn't that going to be r? Well, I think we can figure out r. We know this length, and we know this angle. I think we can figure out r. Do you guys see it? All right, let's do that. Let's figure out what r must be. So I think r is going to be 20 sine 25. Is that okay with you guys? All righty. So now I'll go back over here, and we'll write this again as tan 25 equals v squared over 20. Well, wait, we can't use 20. We'll use 0.2, right? 20 centimeters, but we have to put it in meters because g is in meters, right? G is in meters per second squared. So I have to make sure all the units line up. So I'm going to change that 20 to a 0.2. All okay? Sine 25 g. All right, ready to go forwards? Now, here's where you guys should go forwards, but I want to remind you v equals 2 pi r over t. Right, we're trying to get t. You could substitute right now and put t in there if you wanted. Or you could solve and get a number for v and then use v to figure out what t is. Makes no difference to me, but remember, there's a future where you don't get numbers and everything has to be done symbolically. That future's coming for you. You understand that? So I know it's easier to use numbers sometimes, but that future where everything has to be in terms of theta and the length of the string and stuff like that, that is a real future you'll have to be prepared for. But we'll go ahead and do the numbers. I think that'll make it easier on you guys. So v squared equals 0.2 sine 25 times g, which is 10, times tangent 25. There's no simple way to do that. You just have to punch it into a calculator and get a number. Then take the square root. So I'll give you guys a second to do that, and I'll do it too. I would keep more decimal places in your calculator for this, but for right now, I'm going to write that. So we want to figure out the period. You'll notice that we've left the force stuff way in the background, right? The force stuff just got us those two equations. Everything else has been some amount of algebra, right? All of this is just algebra. But it's a lot of algebra, isn't it? That's the point. That's the thing. The force stuff isn't all that hard, but it's the algebra that follows that can be momentous for some of you. We still have more to go. I got to do some substitution over here. So 0.63 equals 2 pi times 0.2 sine 25, because that's r again, all over t. So I'm just going to cross multiply to get t by itself. So t equals 2 pi times 0.2 sine 25 over 0.63. All right, just math, right? You got to do all the math stuff now. So divided by 2, divided by 3.14159, divided by 0.2, divided by 25. I got my answer. I'll wait for you guys to get yours. Now, as a force problem goes, the force problem was done basically right here. That's when the force problem was done. Everything else was substitution in algebra to get down to there. There's a lot there. But again, it's the force problem, I think, is where we start. Introduce something new. I want you to hold on to that, okay? Are there. Your homework. Anybody know what a record is? They made a comeback for a while, and a bunch of people bought them foolishly. But they're still out there. I still see them. Any of you into records? Good. I'm glad they're still out there. I used to love buying records when I was younger. You go to the record store, you bring the record home. It was big. So the artwork on the front cover was always amazing, because some band paid, somebody to make the artwork. Then the inside had liner notes. I know you guys don't know what those are, but it would be like the lyrics sometimes, which, and how they made the record and other pictures of the band. It was awesome. And now music doesn't have any of that, which I think is a little sad. CDs made it a little sad, but at least CDs came with like a little booklet inside. It wasn't as big as a record, but records were fun. For the longest time, I had lots of them. And then I stupidly sold them all when I moved here. If I had known they were coming back, could have opened a record store. All right, so a record looks like that. Right, it has a little hole in the middle to make sure you center it. Put the needle on the side, and it spins. So, Liam, what are the record speeds? Okay, there are two that are popular, but there was actually 4 over the decades. So there were 78s, there were 45s, there were 33 and a thirds, and there's 16. Now, 16 was never really used in regular production. 78s were used in early records, so we're talking like the 20s and 30s. And then the predominant way of spinning a record was 33 and a third for a long play record and 45 for a short play record. Jukeboxes had short play records. They had one song per side. They were singles. That was how most of your radio stations played music on these 45s. And jukeboxes did too. They had a big hole in the middle. That's how the jukebox would be able to get the record and get it spinning. Long plays had a little hole in the middle. It's a long play, which means it was a 33 and a third RPM. What do you think RPM stands for? Rotations per minute. That's what it stood for, rotations per minute. It's a way of describing the speed of the record. Now, this part I don't think is too big a deal, but it might be for you guys. The whole record spins at one angular speed. There's a symbol we use for angular speed, and it's a fancy looking W, but it's lowercase. And the truth is, it's not W at all. It's a Greek letter again, omega. But we're just gonna say it's a fancy W for the time being. And it's an angular speed. It's a velocity because spinning things have direction too. For right now, we'll just say things like clockwise and counterclockwise for spinning speed. But we'll have to edit that later. Now, that's how fast the whole record is spinning. So that means a point that's right here, it's going around 33 and a third times every minute. And a point over here is going around 33 and a third times every minute. But which one of those 2 points is making a bigger circle? Point number 1 or point number 2? 2. So which point is going faster? So if we want to talk about the linear speed, point 2 is making a bigger circle every minute. Agreed? But point 1 is making a smaller circle. So the linear speed here for point 1 is different than the linear speed for point 2. That all okay? Now, you can probably imagine that there's a way to figure out the linear speed from the angular speed. And it's not particularly hard. One way is to just use this kind of mentality that we were talking about before. This could help us. And I don't know if you see it here, but if you were to section this off, this is taking the time it takes to go 2 pi radians, right? That's what this is saying. That's where the 2 pi comes from for a circumference. But I'm afraid some of you don't know what radians are. How many of you know the phrase, know what radians are? Only a few of you? So many of you have not learned radians yet? I'm afraid you're going to have to learn a little bit about radians. It's going to have to come up. But we can hold off for a little while, okay? Because it's not a big deal. But what I want you to do is I want you to think about if you know something's speed in rotations per minute, could you figure out what its linear speed is in meters per second? I'm thinking this is something I shouldn't have to teach you. I don't know if you can do it or not. Let's say we're talking about a standard record, and we're looking at a point that's not quite on the end, so that's about 10 centimeters from the center. Do you have the ability to figure out how fast it's going in meters per second? I'm giving you lots of things to try. See if you can do it. If you can't, I will provide you a method. But if you can, I shouldn't have to provide you a method. Try. But like I said, if you can't do it, I will provide you a method. If it's traveling 33 1/3 revolutions per minute, I want to convert this to meters per second. Okay? So we're going to handle the minute part and the revolutions part separately. Is that okay? I'm going to use unit multipliers. And I'm going to go with 1 revolution is equal to 2 pi r meters. Right? Because a revolution is a circumference. Does that make sense? And so I know how circumferences work. So 2 pi r is how far it travels in 1 revolution. So this is a unit multiplier that's converting the revolutions to a distance. Any question about that? So this is your first step. Now, how many of you have used unit multipliers before? All right, excellent. If you've never used unit multipliers before, it's no big deal. What we're doing here is we're going to take this part and cancel it and replace it with something else. So each thing in parentheses is considered 1 unit, but it's converting from 1 unit to another. So this one converts from revolutions to meters by using the circumference. This next multiplier is going to convert the time. And for the time, I'm noticing minutes is on the denominator, so I'm going to put minutes in the numerator. And what do I want to convert to? Seconds. Do you have a conversion fact that goes from minutes to seconds? Excellent. All right, this will do it. This uses 2 unit multipliers. One that converts revolutions to meters, and one that converts minutes to seconds. And this is going to give us something in meters per second. I will need the radius, though. Do we have the radius? And I will have to put the radius in meters, so I can be in meters. But that's not too hard. Our radius was 10 centimeters, so that's 0.1 meters. All good? All right. So you can convert that pretty straightforward like to give me meters per second? Excellent. Excellent. So Christian, what do you get? 0.35 meters per second. Sounds about right to me. Anybody else get 0.35? I think that's what we should get. All righty, 0.35 meters per second. Oops. So, you're wondering why I'm going through this. I'll tell you why. There is a spider on the record. The spider's holding on with his little spider feet, hoping he doesn't fall off. What coefficient of friction does the spider feet have to have between the spider and the record so that the spider stays on the record? I want to work this question out. I think this is a good one. What kind of friction are we talking about here? Static. So we're going to be dealing with static friction. All good? Ready to go with this one? You guys ready? I think we can do it. How many forces must be acting on the spider? I think 3, but I don't want to draw it the way it's drawn now. I want to draw it from the side. Is that okay? So I'm going to draw it from the side. Somebody's making noise. Those sound like phone noises to me. I'm going to ignore it, because the bell's going to ring soon and you'll all be happy to leave. So there's my spider. Name a force acting on the spider. Okay, excellent. Weight. Name another force acting on the spider. Name another force acting on the spider. What direction should I draw static friction? Now this one's hard, I think, but there has to be a force acting on the spider to cause it to travel in centripetal motion. By definition, this unbalanced force has to be towards the center of rotation, or the spider can't travel in a circle. I know that your instinct is to say that the force is to the right, but the force in this case has to be towards the center. That has to be the direction of the frictional force. Again, your instincts here aren't always going to be correct, but the unbalanced force has to be towards the center, and the only unbalanced force left is friction. Friction is going to provide the centripetal force here. Now going forwards, this is still just going to be a standard force problem with net force in the x direction equal to ma and net force in the y direction equal to 0. I think we all know this is going to be normal equals weight on this side and friction equals MAC on this side. Now this part of the problem just kind of falls back into place like the other ones, except it's a friction problem and it's using static friction, and static friction is an inequality. Whenever you have an inequality, it's always best to substitute into the inequality. So that's what we're going to do here. MAC must be less than or equal to mu times the normal force. So I'm thinking m v squared over r has to be less than or equal to mu mg. Do you see a pathway where you can figure out what mu is? You have v, you have r, you have g. I think you can do the rest of this problem on your own. Anybody ever slides? They don't really have them at theme parks so much. You guys know what I'm talking about? One of these spinny rides where you kind of stick to the wall. So they had a ride like this at Busch Gardens years ago, but they don't have one like it now. But do you guys know what I'm talking about? Yeah, they call them different things, Graviton or Gravitron or something. If you go to like the state fair, they'll have them. It's basically a big closed-in ride. It spins really fast, and you can be like that, and the floor drops out from underneath you, so you're like suspended against the wall. They're a lot of fun until suddenly they're not a lot of fun. It really depends on what you've probably eaten that day or within the last 20 minutes of getting on the ride can really determine the kind of ride you're going to have. There's other versions of it too. There's the ones that are big and open, and you have like just a pad behind you, and you have a little cubicle that you stand in with a little fence in front of you, and then the whole ride spins up and starts to turn on its side like that. Have you seen those? Same kind of ride, except the floors don't drop out of these. Generally, just standing there, but you get the impression that you're going to be, oh my word, I'm going to fall. No, you're not. You're not going to fall. In these rides, you are going in a circular path. What forces do you think are acting on you? Gravity. How would I draw that? Okay, what else? There's a normal force, but how would I draw the normal force? What keeps you from sliding down the wall? Friction, yeah. Yeah, what kind of friction is this? Can you see, I guess if you spin the ride fast enough, get enough normal force, you can probably not slide down the wall? If I was to ask a quiz question, I think you've seen questions like this on there. I do have the answers all worked out with the solutions. I'm just going to post them for you guys so you can have the solutions to look them over, okay?